Hello, everyone, and welcome to the JISEA virtual meeting. My name is Jill Engel-Cox. I'm the director of JISEA, the Joint Institute for Strategic Energy Analysis, and I appreciate all you being here for our virtual meeting. So I'm going to go over an overview of the agenda and JISEA, but first I'm going to turn it over to my colleague Vicki Healy, who's going to be showing us some webinar logistics. So Vicki, why don't you go ahead and go through that?
Great. All right, great. Thanks, Jill. So hi, everyone. Welcome to this virtual meeting. We're all excited to have you here. Just a couple of things I want to go over regarding the webinar functions. Just to let you know, as far as audio is concerned, you have a couple of options. You may listen through your computer or over your telephone. And if you choose to listen through your computer, please select the mic and speakers option in the audio box. If you want to dial in by phone, you're welcome to do so. You just need to select the telephone option, and a box on the right side of your screen will display the telephone number and also an audio pin. So again, just a real quick gentle reminder to our panelists, while you're not presenting, if you'd please mute yourselves, that will help with eliminating background noise. Next slide. And just to illustrate the features a little more clearly for you all, we've taken a screenshot of an example of the attendee interface. So you should see something that looks like this in the upper right corner of your screen. We will have a question and answer session, so you can submit your text questions to the presenters by typing your question into the questions panel, and you can send your questions in at any time. Jill will be collecting these questions and will present them to our panelists during the Q&A session. And when you submit your question, please include the name of the presenter that you are addressing your question to. So with that quick overview of our webinar features, I'll turn things back over to you, Jill.
Thanks, Vicki. I'm going to start out with just a quick review of the agenda. The way we're running this meeting is as if we were having a virtual meeting where you would attend a series of presentations. So I'm going to spend this first 5 minutes or so giving you a welcome and introduction to JISEA. Then we'll have 2 themes with 3 presentations each. So starting about 9:05 or probably about 9:10, we're going to start with the power systems theme. And then we'll have 3 presentations, and then we'll have, starting about 10:30, we'll have an industry and agricultural theme. This agenda was sent out to all of you, which has more details on each of the presentations if you would like them, and I will introduce the speakers as we go forward. But first, I want to start out with a little bit of introduction to NREL and the Joint Institute. So NREL is the National Renewable Energy Laboratory, and we are located in Golden, Colorado, beautiful sunny Golden, Colorado today. About 2,300 employees with many postdoc researchers and visitors. And we have 2 main campuses. The main campus, which we conduct research on a wide variety of energy, renewable energy and energy efficiency. You can see many of those topics there on the picture of our campus. And then we also have a Flatirons campus where we conduct manufacturing research in full-scale wind research. NREL is one of the members of the Joint Institute for Strategic Energy Analysis, along with 5 universities, MIT, Stanford, Colorado School of Mines, Colorado State University, and University of Colorado Boulder. And we were set up about 10 years ago in order to look at a systems approach, power systems, supply chains, industry, human systems, ecosystems, and how these technologies, economics, and places all around the world are working together to look at the clean energy economy. And this was really set up to be able to connect the renewable energy sector with other types of energy sectors and international transitions. We bring together a wide variety of partners and collaborators from the private sector to government to foundations to work together to put together consortiums to conduct projects that intersect these different types of organizations and their interests. And you'll see some of the projects presented today were funded by consortiums of collaborators on a variety of different topics. Our portfolio covers a variety of different topics as shown here. Clean industry for industry and agriculture, so exploring how clean energy can support these new sectors. Energy systems integration and transformation, how different types of energy work together. Advanced manufacturing analysis, and we'll hear some of those topics as well today. And then a focus on international collaboration and capacity building. So you can learn more about these topics on our website, and we just released our 2020 annual report yesterday. So if you go to JISEA.org, you can find our annual report, as well as on our publication site, you can find detailed on all the publications and research that we are conducting. And I want to mention, though, in conclusion about JISEA, is that we're really all about the people and collaborations. And although we can't be all together in person right now, the opportunity to work together with the researchers from across NREL, across our collaborating universities, across our industry and government partners, that is really what makes JISEA a unique organization, and is what makes our research so exciting, I think, to really bring together different types of people to collaborate. So going back to the agenda, just a reminder, we will be starting with our power systems theme first. We will start with a presentation from Travis Lowder and Jeff Logan on utility offerings. Then we'll be moving to looking at resilient power systems in South America. Jeff Logan and Josue Prado will be presenting that. And then that theme will be power. The theme will end with power and natural gas systems from Bri-Mathias Hodge. Then at 10:30, we'll be focusing on industry and agriculture, including renewable energy and mining from Travis and TC. We'll be looking at supply chains for LED lighting from Samantha Reese. And then we'll be looking at the energy, water, food nexus from Jordan Macknick and James McCall. So again, I want to thank all of you for being here and joining us. Please do feel free to join us to remain for all of the 6 presentations. You are also welcome to join us at any point for any of the individual presentations. So we look forward to moving forward with these topics. Please also remember that you can type questions in the question box during any time, and I will be facilitating the question sessions as we go forward. So I'd like to go ahead and turn over the controls. Vicki, back to our first presenter, which is Travis Lowder, who will be talking about innovative utility offerings at the distribution edge. And so, Travis, whenever you're ready to start, please go ahead.
All right, thank you, Jill. I'm just gonna toggle my screen here to make sure. There we go. Can you all see the presentation?
I think you need to do your.
Yes.
Oh, I cannot actually, so I think you need to show your full screen, not just PowerPoint.
Okay, let me. Sorry, we're all still sort of navigating the technology wonderland. I will.
I can see it now. Thank you.
Oh, okay. Sorry, I just stopped. Let me try again. Okay, is that showing up for everyone?
Not
Yes.
yet. Did you receive? Oh, you have it. Okay, thanks.
Yes. Jeff, you said you can see it. You can see the presentation, not in the slideshow mode, but in the full screen. Okay.
I see it. Yes.
Yes, we can see it.
Great. I'll just plow on ahead then. Thank you, everyone, for joining us today. Obviously, it would have been great to see you all in person, but I'm glad that we found a technological solution to get us all together today to talk about JISEA and what we've been doing over the last year. So Jeff Logan and I are going to present on innovative utility offerings. This is based on a paper that we wrote that was presented at the Clean Energy Ministerial in Vancouver of 2019. And so we're just going to give an overview of the research we did for that paper, and we'll take your questions at the end. Real briefly, just to introduce ourselves, I am Travis Lowder. I've been with NREL for about 7 years. My research career has been based mostly in renewable energy policy, finance, and regulations. Jeff, who will be speaking in the back half of this presentation, has a background in clean energy policy analysis that spans about 30 years. He's worked with prestigious organizations such as WRI and the IEA, and he's been with NREL for about 12 years now. As I mentioned, this is all based on a paper that Jeff and I wrote. The paper is accessible here. I believe we will be providing these slides afterwards, so you will have this link, but feel free to Google this and read along if you'd like. Apologies here, I'm just trying to, I've got a freeze, there we go. So just to set some context for the paper, we're really looking at this topic because we've arrived at this present day where we've got a profusion of DERs in certain areas of the grid. We've got this phenomenon known as prosumerism, which is where consumers can not only purchase electricity, which has been their traditional role, but also produce electricity that can feed back onto the grid. And utilities are really experiencing a changing paradigm, not only in how they manage the grid and how they plan for it, distribution grid, excuse me, specifically, but also in how they are operating it. So the history here is really that coming out of the late 1800s, you've got this utility business model that's starting to solidify. Samuel Insull was a major influencer, visionary in this respect, imagining utilities to be organized around the central station generation concept and the economies of scale that these utilities can achieve. And the fact that these economies of scale allowed for natural monopolies. It made more sense for them to sort of be the sole providers of the service. Through the 1920s, you've got over 1,000 IOUs vertically integrated being incorporated, and these regulatory compacts being formed with various jurisdictions where the utility provides service to anyone that asks for it in exchange for having their rates approved by the regulator, the state regulator. Really, during this time, the principal regulatory precepts were safe, reliable, and low-cost electricity service. And then moving into the 1990s, this model largely preserved. But then, as we're all sort of have memory of, in the mid-1990s, we started to look into, in this country and in others, restructuring where transmission and generation were sort of divested from the utility. The utility had control of the distribution system. And in some jurisdictions, you had retail choice, where the utility was no longer the sole provider of electricity service, even if they were the provider of supply. And so moving on from there into the present, the next big change was the one that I started with, where you have the profusion of DERs, and the regulatory compact is changing somewhat. The safe, reliable, and low-cost service is no longer, in some places, the only considerations in the regulatory compact. You've got things like environmental concerns and consumer choice, customer empowerment, energy equity. All these things are changing the game. And utilities are now having to compete against third-party service providers that are providing DER services. And it's a different game for them. So this report is really about how the utilities are innovating around new products and services that will allow them to continue to generate revenue and really access customers in a way that they've never had to before. So we spoke with a number of utilities for this report to get a sense of what they were doing. Before I launch into what the products we focused on were, I will just say that some of the themes that we lifted out of these conversations were that the utilities are very interested in continuing customer empowerment, but in a way, obviously, that's where they can reach the customers. So it's not just providing them third-party services through solar and storage, et cetera, but also in allowing them to provide products and services directly to customers themselves that are outside the utility, standard utility customer relationship. They can do this in a way that allows them to contribute to system-wide goals. For example, one utility that we interviewed had a program where they had an electric heater, centrally controlled electric heater pilot, where the utility provided these control units like a Nest thermostat for electric heaters. And they ran a control trial where they turned some of the heaters up right before the peak period and were able to realize some system-wide depression in peak load. These are things that when the utilities plan, they can not only offer customers new services and products that may save the customers money, but they can also reduce peak load and contribute to other system-wide goals. The utilities are also interested in addressing their specific market contexts. So Jeff is going to talk about an innovation from TEPCO in Japan, which addresses the aging population of that country specifically. We looked at another innovation from a utility in Africa that was a concessionary loan structure for energy access, providing meters for an alternative pay structure than what you might have under a standard loan. Obviously, utilities are also looking to reduce emissions. This has become not only a goodness of your heart thing, but it's also an environmental societal governance thing, and in some cases, a regulatory thing as well. As I mentioned, this all sort of has its genesis in the fact that utilities are having to compete now in a way that they never have before. And so innovation is sort of necessary. It's incumbent on them to sort of survive in this new era where we see a changing distribution grid and changing energy practices on behalf of consumers. So these were the innovations that we looked at in this report. We've broken them out by category on the left axis there, energy supply, energy efficiency, et cetera. And then we tried to do a sort of comprehensive around the world look at these innovations in these utilities. So up at the top there, you see that we tried to break it out by continent to give a global view of what's going on in this space. The innovations we're going to focus on today specifically are highlighted here. Jeff's going to kick things off with TEPCO as I pass the slide over. So Jeff, I'll let you go off mute here, and I can maintain control of the slides, but why don't you go ahead and we can dive right into the innovations we're going to be discussing today.
Great, thank you very much, Travis. So we're going to deal with 4 quick case studies here, and we're going to begin in Japan with the Tokyo Electric Power Company's elderly care plan. And given the fact that there are so many elderly people in Japan, and they often live by themselves, the utility came up with an idea to help the children of the elderly keep track of how their retired parents are living. And it's kind of like a way to snoop on your parents to ensure that they're living a healthy lifestyle and that they're doing everything that they should be doing. And so the utility offers to the children a special product which costs roughly $25 a month, so that they can see when the parents are using their dishwasher, their air conditioning, any other big appliance in the home. And then they can know whether or not their parents are taking showers at the right times, and whether they're eating properly and things like that. So it's a kind of an interesting approach. And we really enjoyed learning more about this innovative offering from Japan. And what makes it unique is that you do not need to have a smart meter to disaggregate which appliances are being used at which times. So if you go to the next slide, Travis, you can see what this electronic device looks like that keeps track of which appliances are being used and when and for how long. So it's a real simple update that needed to be made to the electronics in the home, and it excluded having to use a smart meter, which is, smart meters are available in many millions of homes around the world, but they're a lot more complicated than what was used here to provide this innovation. So the other thing that this utility innovation offered is a backdoor to do a lot more energy efficiency thinking for how customers use energy and what upgrades could be made to enable more efficiency. So that's briefly the TEPCO experience. And then if we go to the next slide, we will go to India, where this utility called BSES Rajdhani is located just outside of New Delhi. And they've introduced a behavioral energy efficiency program there. This is the first time that we're aware of a behavioral efficiency program being introduced in a developing country. They obviously exist all over the industrialized world, but it's the first case where India tried this approach. And it's a pretty simple idea. They give a home energy report comparing the homeowner's energy use compared to its neighbors and compared to people who are considered highly energy efficient. And that will hopefully incentivize them to pay much more attention to the way that they use electricity and other forms of energy in their homes. So there's a pilot that's currently ongoing, and the company O Power is a partner with the utility in this. And if we go to the next slide, we'll see an example of what the behavioral incentive is here. It's really just looking at the home energy report, which compares the individual's electricity use compared to other homes in the area. So we'll move on from that to the third example, which is in the state of Washington, where Puget Sound, which is the largest investor-owned utility in the state of Washington, has rolled out a program called Green Direct. And, there are a lot of companies in Washington state like Microsoft and REI and Target that were clamoring for something more than just a community solar program or a green tariff. And so the utility took great interest in keeping them happy and met with the regulator there to ensure that what they were going to do was just and reasonable. And they designed a program that would provide the benefits of things like community solar, but it would include the cost effectiveness of doing it at the utility scale. So they offered these companies and institutions a chance to own part of a new and local renewable energy project that locked in long-term fixed prices and contracts that would hedge against any fuel price volatility in the future. And the utility also met with the Renewable Energy Buyers Alliance stakeholders to ensure that they were checking off as many of the boxes they could on how renewable energy should be purchased and how the RECs should be controlled. So that is I think an interesting grid scale utility offering that Puget Sound is providing. And then finally, if I think we'll pass this next graphic and go on to Canada, where in Alberta, ATCO is a energy and utility provider there. And they partnered with the city of Lloydminster to introduce a wireless street lighting pilot. And it provides, this is a system where all of the street lights are interconnected through a wireless network. And the lights only come on when either a pedestrian or a driver is approaching the light. And so they got rid of all the high pressure sodium lamps that were on the system and replaced them with LEDs, and then interconnected them all together with this wireless network. And it resulted not only in a huge savings in their energy use, but also in the maintenance costs that are required to service the high pressure sodium lamp system. And I think everyone probably knows what these high pressure sodium lamps look like. They have horrible color rendition compared to an LED bulb. So you're not only getting these cost savings, but you're improving the light quality enormously. And they won an award from the Illuminating Engineering Society in 2018 for this rollout. In the future, these lighting systems have a chance to become an Internet of Things for mobility, because they can wirelessly keep track of who is approaching and provide perhaps even customized advertising to tourists, for example, who are visiting, and also informing other local residents of any important news that might be breaking. So I think we have one more graphic to show a little bit about what this wireless lighting pilot project looks like. And you can see that the lights and the pedestrians and vehicles are all interacting through the wireless network. So with that, those are 4 very quick snapshots of the 10 that we looked at that are in the report, and I encourage you to access the report and read up more if you're interested. And with that, we'll stop and see if there's any questions.
Thank you, Travis and Jeff. And Jeff, you're up next, so you might as well start getting your new presentation. But we do have one question. There's a question about privacy issues, specifically around the Japan and India study. Were there concerns at all about privacy, or do you think there's maybe differences between what countries can do based on different cultural values around that?
That's a good question. We did not really dig deeply into that issue, but my assumption is that in Japan, that was a priority concern that they looked into while they were designing the program. In India, I don't know. I'm not sure that there's. I know that they randomized, like they do with any kind of behavioral energy efficiency program. They randomize what they consider the control groups or the comparison groups. So I don't think there's any concern with revealing private or sensitive information in that sense.
Okay, great. Thank you very much. We're going to go ahead and go on to the next presentation, which is Jeff Logan as well as Josue Prado, and going to talk a little bit about the resilient and flexible power systems in South America. And I'm seeing some new questions come in. Please keep sending your questions in. Since it's Jeff presenting again, we may have some questions related to the last presentation. So I will go ahead and turn it over to you, Jeff, and then we will cover questions at the end of your presentation. So also the attendees, please keep sending those questions. Thank you. All right, Jeff.
Thanks, Jill. And sorry again, everyone, you're going to have to hear my voice again for a few more minutes, but Josue will be doing the second part of this, and I'll be doing the first. So we were asked by the Department of Energy about a year and a half ago to conduct a study of key countries in South America, ones who are heavily dependent on hydropower and ones who also have rapidly growing shares of variable renewable energy. And we were looking at the question of how can these countries best deal with uncertainties that are associated with the El Nino and La Nina phenomena that results in either less or more rainfall happening. And in Brazil, for example, in a recent meteorological year there, they lost almost 20% of their typical hydropower generation. So in cases like that, what do these countries do to ensure that they can continue to deliver electricity to their customers in an affordable and sustainable and reliable way? So that was like the impetus for our study. And let me see if I can advance these slides. I'll just note that Josue was the main author of this work. He is currently just about finished his PhD at the University of Nebraska and Lincoln, and he is a power system planning and operational expert, and he did a fantastic job, I thought, with this report. So what we're going to look at here, I'm going to cover this first bullet that deals with global power system transformation and talk about the need for flexibility in these key South American countries. And we're also noting that natural gas is one of the powerful options that are available to these countries to deal with situations when they have either a lack of rainfall, or in some cases, they might have too much. So we're going to look at that. And then Josue is going to then look specifically at the 4 countries and think about some of the options that are available there. And these 4 countries include Argentina, Brazil, Chile, and Colombia. So
Jeff, are you still there?
here that shows decarbonization, digitization, and decentralization that is pushing some of this transformation along. And what's central, I think, to the transformations that are happening is the need to think about flexibility in a new way. And flexibility includes both having affordable and efficient market design, but also reliability and resiliency concerns. And I think as we've seen how the coronavirus has impacted electricity system planning and operations already by a significant amount, these things are going to become more prominent and important in the future going forward, I think. And the need to provide flexibility has to be looked at from both a short-term and long-term perspective. So you can see here in the bottom right, the graphic shows how you can think about providing flexibility even from the sub-second level to the long-term month-to-year and seasonal approach, seasonal considerations. So as I noted earlier, there's definitely an increased focus on the need for flexibility in certain South American countries. And we have shown here the power generation mix from these 4 countries over time. And what we can see certain things in each country. I'm going to start by just looking at Chile. which, as you can see, has hydropower, coal, natural gas, oil, and biofuels, wind, and solar listed there. And you can see that starting around 2005, the amount of natural gas that was being used in Chile to generate electricity shrunk rapidly and was replaced by oil. And then slowly over time, they built more and more coal plants in Chile. And what happened in that country is that around that year, 2005, Argentina cut off its supply of gas to Chile. So they had to scramble to find new ways to replace that lost generation. Similarly, in Brazil, the El Nino that hit in the year 2014 through 2016 lowered the amount of hydro available significantly. And Brazil also had to come up with new sources of generation to meet that lost generation potential. Argentina is less dependent on hydropower and more on natural gas. And as we'll learn later from Josue's section, Argentina is home to the Vaca Muerta formation, which has the potential to produce an enormous amount of natural gas and oil. And it's under development right now. And it'll be interesting to see how that evolves, because it will have important implications for many countries in South America. And finally, Colombia is very heavily dependent on hydropower. And it also, like the northern part of Brazil, it is susceptible to the El Nino years, where hydropower availability can decline significantly. So with that, we're going to move to the next slide and look at the framework that we used for thinking about flexibility needs in South American countries. And so there are hydropower, renewable, and thermal power generation options. Each one of them has issues associated with it. And then within the electricity sector and the natural gas sector, there are a whole bunch of different policy options that are available to decision makers to improve flexibility and think about sustainability and reliability and resiliency. So that's, in a nutshell, the kind of approach that we took to thinking about flexibility for each one of these countries. And then, as I noted earlier, natural gas has played an increasingly important role in providing flexibility for most of these countries. And you can see that in the slide on the left, natural gas consumption for power generation reached its peak in the years 2014, 2015, when that El Nino severely impacted hydro availability in South America. And so a lot of countries in South America ramped up their LNG imports during those years, and they have since come down since then a little bit. But as I think everyone on the call probably knows, that the coronavirus has significantly reduced the cost of LNG, or lowered the price of LNG around the world. And I'm sure countries that feel vulnerable are looking very carefully at purchasing more LNG in today's world, because it has become extremely cheap. So with that, I'm going to turn it over to Josue, who will take a closer look at some of these countries. And I can continue to advance the slides for you, Josue.
Thank you, Jeff. So my name is Josue, or Josh Prado, and I'm going to present our country-specific analysis, which includes the main drivers of the need for flexibility and some policy options in both the electricity and natural gas sectors. Next slide. So let's start off with Argentina. So Argentina is the most dependent country on thermal power generation in this study, as you can see in the figure showing the installed capacity. And Argentina faces several challenges, especially in direct investments in the electricity and natural gas infrastructure. This is due mainly to the shrinking economy, high inflation, the depreciating peso, and also decades of markets distortions associated with subsidies. Next slide. So some of the drivers of the need for flexibility in Argentina include rainfall variability in lesser extent than Brazil, Chile, and Colombia, as Jeff mentioned before, but it's still significant. As you can see in the impact of a La Nina period in one of the main reservoirs in the country on the left-hand side figure. Also, the growing VRE integration, especially motivated by the successful Renovar auctions, are still challenging the system flexibility and also highlighting the need for more transmission infrastructure. So the auctions were successful in terms of market outcomes, but these auctions also highlighted the need for more transmission and distribution infrastructure. And also we need to talk about the thermal power inflexibility and fuel supply uncertainties. For example, in years when natural gas was not widely available in Argentina, the country had to resort to an expensive fuel such as gas oil and fuel oil. So you can see in that right-hand side figure on the bottom of this slide, in the years of 2010, 2011, 2012, the high use of fuel oil and gas oil, which are very expensive fuels. Next slide. So this slide shows the Vaca Muerta shale formation in Argentina, and this formation holds the world's second largest shale formation and has the potential not just to supply Argentina's needs, but also, allow Argentina to export to other countries in South America via pipeline or even LNG to Asia and other markets. However, there is a challenge in attracting upstream investments and also building the necessary infrastructure to move the gas to the market. So with the low oil prices now, it's getting really challenging for Argentina to produce more natural gas and find ways to monetize this gas. Next slide. So here we show some policy options in both electricity and natural gas sectors. I want to highlight the demand response and distributed energy resources in the electricity sectors, and especially to reduce the dependency on centralized solutions. Of course, these options should be followed by transmission and distribution infrastructure upgrades. And in the natural gas sector, the country needs some investments in underground natural gas storage, especially to mitigate seasonal imbalances. So you can see the seasonality of gas demand in the figure on the right, the upper right hand side. The production is slowly increasing, but the natural gas demand is very seasonal. So this is a big challenge, and we believe that natural gas storage, especially underground storage, might be a good solution to overcome this issue. Next slide. So let's talk about Brazil, my home country. So Brazil continues to be dominated by hydropower. However, you can see that the share of hydropower generation is decreasing, as Jeff already mentioned. So in 2028, hydropower generation accounted for 75% of the total generation in Brazil, but in 2018 accounted for only 64%. So Brazil has very good energy planning capabilities and has developed several long-term auctions for wind and solar power, and very successful auctions. In the natural gas sector, Brazil is developing its offshore resources, especially from the pre-salt fields. And the country is also introducing market reforms to monetize this gas and finding ways to better integrate natural gas in the electricity sector. Next slide. So some of the drivers for the need of flexibility in Brazil include the rainfall variability, especially due to both El Nino and La Nina. So Brazil is affected by both, El Nino, especially in the north part of the country, and La Nina in the south. Also, the greater adoption of the run-of-the-river power plants with smaller reservoirs, and the growing VRE integration. And very interesting in Brazil that the VRE integration is both centralized and also distributed. Next. So here we show some policy options, and I want to highlight especially the pricing mechanisms in the electricity sector. So Brazil is currently working to implement the hourly spot prices. Right now, they still have the weekly prices, and I believe the hourly spot prices will be very important in terms of flexibility. And in the natural gas sector, investments in offshore pipeline infrastructure, especially in the pre-salt fields, along with underground storage, flexible LNG contracts and technologies, will also play a big role in terms of power system flexibility. Next slide. So let's talk about Chile. So as you might know, Chile was one of the first countries to introduce market-oriented liberalization and privatization in the electricity sector. And as Jeff mentioned, it has relied on coal and oil products in the electricity sector to make up for the lost gas supply from Argentina that started during the 2004 gas crisis. But Chile is now committed to phasing out coal generation by 2040 or even 2035. And Chile has great wind and solar energy resources. So wind resources in the south and wind in the south and solar resources in the north part of the country near the Atacama area. But however, the geography of Chile and the social distribution makes it very challenging in terms of flexibility. So Chile has a very interesting longitudinal extension. The population is concentrated in and around Santiago, and there is a high electricity demand from mining centers, especially during the night when there is no solar power production. So the geography of Chile is very challenging in terms of planning and also the infrastructure. Next slide. So here we show some of the drivers for the need of flexibility in Chile, and we also have the rainfall availability, seasonal and also long-term. Seasonal is mainly special due to the La Nina phenomenon. We also have the increasing adoption of run-of-the-river power plants. This is very interesting data. So in 2028, run-of-the-river power plants accounted for 36% of the hydropower plants, and now in 2018, it accounted for 68%, and this number is growing fast. And also the increasing VRE adoption. So Chile also has some interesting market mechanisms for VRE. Next slide. So here we show some policy options in both the electricity and natural gas sectors. And we believe that demand side management, distributed energy resources, along with storage systems will play a big role in the electricity sector in Chile. In the natural gas sector, the country has insufficient gas reserves, especially to be developed over the long term. So in natural gas import diversification and flexible LNG contracts may help the country to achieve greater flexibility. So flexibility, power system flexibility is very important in Chile right now. Everybody's talking about that and trying to find ways to combine different sectors and ensure that the system is resilient, reliable, and flexible. So let's talk about Colombia. Colombia is the most dependent on hydropower in this study, and it is the most exposed to El Nino. So Colombia is located in the north part of South America, and it's very, very affected by El Nino. So domestic natural gas production in Colombia is decreasing, but the demand is growing fast. So the country is trying to find ways to solve this issue. So, and among the countries in this study, Colombia is the only one that does not have a vibrant market for variable renewable energy, but it is working to develop long-term auctions for VRE. And the first auction was held last year and was successful. So it's good news. Next slide. Some of the drivers for the need of flexibility in Colombia included rainfall variability, especially during the El Nino seasons. So on the left-hand side, you can see a figure showing the hydropower capacity volume during an El Nino year in red, a La Nina year in blue, and a neutral year in black. So you can see how the capacity volume went down during the El Nino and went up during the La Nina. And you can see that the neutral year is in between both curves. And on the right-hand side, you can see how the electricity spot prices were impacted during the period with lower hydropower generation. So this is a big issue that XM, which is the electricity market operator in Colombia, is trying to find new ways to avoid these spikes and prices during these periods with lower hydropower generation. Next slide. So here we show some policy options in both the electricity and natural gas sectors. I would like to highlight the importance of generation mix diversification in Colombia and effective pricing mechanisms in the electricity sector. So XM is working hard to find new ways to define markets for flexibility, reliability, and resiliency. So they're working hard to make sure the electricity market is prepared for the next changes in the country. In the natural gas sector, import diversification and flexible LNG contracts may also help the country to achieve greater flexibility. Next slide. So here we show the main risks and constraints for more flexible power generation in the countries. For example, Brazil and Colombia are the most affected by seasonal weather events, then Argentina and Chile. But on the other hand, Argentina is the most impacted by fuel supply uncertainties. So this is very interesting because each country has its own problems, but you know, some of these issues are common to all countries in this study. Next slide. And here we show some barriers and challenges for both the electricity and natural gas sectors in those countries. In our report, we discussed the barriers and challenges in more details for each country. So if you are interested, you can take a look at it. There are many challenges and barriers, and some of these are specific to each country, and some of these barriers and challenges are common. For example, transmission capacity limitations, lack of market mechanisms to promote flexibility, and also in the natural gas sector, pipeline capacity, lack of underground storage infrastructure, and so on. And next slide. So finally, here we have our conclusions. I want to highlight the last two bullets. So in addition to the policy options described in this study, in our report, we also mentioned that the international community can offer a variety of assistance and cooperation opportunities to enhance power system flexibility and resiliency. So there's a lot of tools that are available that can help these countries to, you know, develop energy planning tools and options for the future. And also the last point is that on a positive note, each of these countries are developing goals for making their electricity sector cleaner and more sustainable. So this is very good news. So I think with that, we conclude our presentation and happy to answer any questions that you might have.
Great, thank you very much. We have a couple questions, one which I'll answer, which was about the reports available for these presentations. We will be making the reports available, but note also that there are links to the reports for many of these presentations in the agenda. So if you received your agenda, it's also available on the handouts side over there. If you open that up, when we have a report available, you can click on those links and actually see the reports or the website. And this particular study has an excellent report and a highlights study that you can all look at. But we also had another question. It was regarding microgrids and that there might be an increase in microgrids resulting from the pandemic, but also in general. What are the possible implications of microgrids on the studies in the countries that you discussed? Are there certain places that might work well, and how would they actually potentially resolve some of the issues you mentioned?
Josue, you want to take that one?
Yeah, so microgrids is a very interesting topic, and I've seen a lot of utility companies, and you know, not just utilities, but other research organizations developing solutions. For example, in Brazil, there is a lot of utilities working on microgrids. So there are still some challenges, especially in terms of regulations and policies. But I've seen also the regulatory agencies working with universities and other organizations to facilitate the implementation of microgrids, and also developing some tools, standards, and they are looking at all aspects of the implementation of microgrids. So I think it's very important for these countries in terms of flexibility and resiliency. And I've seen a lot of progress lately in all countries in South America, especially Brazil and Chile are investing really hard on microgrids.
Great, thank you. We have another question. Why did the study choose those countries? Why were those 4 countries chosen? And what were the barriers? What are some of the key barriers that they had to overcome?
Okay, I'll start on that one, and Josue can chime in if needed. Well, we picked those countries because, as I noted in the beginning, they're all heavily dependent on hydropower, and they all have growing sources of variable renewable electricity. So therefore, they are most sensitive to any meteorological changes that occur during El Nino and La Nina years. So, some of the barriers that we faced in conducting the study, well, one of the things that we did was Josue and I traveled to South America, and we visited with both government officials and with private sector companies and held pretty detailed interviews. And because Josue is from Brazil and speaks Portuguese and Spanish, we had access to all of the domestically published information from those energy ministries and organizations in each country. So in that sense, it was pretty easy for us to access direct material. I don't know, Josue, do you have anything else you want to add to that?
I think that's it, Jeff. So in terms of challenges and barriers, there are some common challenges and barriers and some specific ones. So in terms of common challenges and barriers, I would say that, for example, market mechanisms to allow greater flexibility, it's a big challenge. So I see all these countries trying to reform the current electricity market to adapt to these changes. So they are trying to develop new pricing mechanisms and new markets to allow not just centralized generation and consumption centers to participate in flexibility, but also distributed energy resources. So some policies and market mechanisms are not developed yet. So this is one of the main challenges. And we also talk about infrastructure. So some of the countries, they lack infrastructure in the electricity sector. And there are also challenges in the natural gas sector, especially for Argentina and Brazil in terms of pipeline and underground storage. So yeah, but in our report, we describe all the main barriers and challenges for each country, and also the common challenges that they are facing.
All right, great. Thank you very much. The people that are sending questions in, if we don't get to your question, because I do want to keep us on time, we will review the questions later and have the authors get with your questions. If you're not a speaker, please put yourself on mute. I'm going to go ahead and turn it over to our next talk, which is our speaker is Bri-Mathias Hodge, and this is a very exciting project that we are in the process of. We do not have a report on this yet, but they are coming soon. And this is the linkages between the power sector and the natural gas pipeline network. So Bri, I'm going to turn it over to you.
Thanks so much, Jill. So just a quick introduction on myself. My name is Bri-Mathias Hodge. I'm Chief Scientist in the Power Systems Engineering Center. at NREL, as well as an associate professor in the Department of Electrical, Computer, and Engineering, and a fellow of the Renewable and Sustainable Energy Institute at the University of Colorado. And so I'd like to talk today about this power and natural gas systems interface study that we've been conducting over the last few years. As Joe mentioned, we are getting ready to publish the final report on this. We actually just had last week as well, the first of a couple journal articles be accepted into energy policy on this study. And so we'll talk a little bit about some of those results today. I'd like to just go through sort of the motivation for this, why the natural gas and electric power system are becoming more sort of reliant on each other, talk about our approach to studying this versus some of the other approaches that one might take, look into the coordination framework that we've developed, talk about our case study on the Colorado electric and natural gas systems, and then finally wrap things up. And so the natural gas and electricity sectors are becoming increasingly reliant on each other. Just as an example, the power system now plays a much larger role in natural gas demand, so increasing dramatically over the last few years. This also is true for the other side. So cheap natural gas has also led to the share of power generation increasing from 2000 to present, from about 14% to now being the dominant electricity generating technology. Concurrently, we've also seen a large increase in the amount of wind and solar power coming onto the power system, to the point where we are now at, in the United States wide, about 7 to 8% wind power and about 2% to 3% solar power. And because of this, because wind and solar are variable and uncertain, we are now looking at a very different power sector than we did even 10, 20 years ago. And what this leads to is these systems perhaps weren't built to sort of look at these large interactions between the two. And this can lead to situations where reliability issues on one system can have reliability issues on the other. So there's this increasing dependence between the two. One classic example of this is the 2014 polar vortex, which led to, there was so much demand for natural gas from the other customers there, from the residential commercial customers for heating, for example, that there were gas sort of delivery issues to power generation. So one key thing we have to keep in mind here in the United States, the contracts for most of the residential and commercial natural gas customers are guaranteed contracts. So you have to be able to deliver that gas to them. Whereas on the power system side, those contracts allow for interrupting the service if there is a shortage of natural gas. And so this key difference in that contracting between the two different types of customers, the so-called city gate customers versus the generation customers, leads to different impacts on the power system as well. So when we're talking about this coordination between electricity and natural gas, there are a number of different sort of ways we could look at this. One is you can look at it at different decision-making levels. For example, at the planning level, looking to optimize the location and capacity and timing of investments associated with generation, production, transmission, or storage in each of these two systems. What we've done here is instead we're looking at the operations of these systems. How can we improve the reliability of these two systems? How can we minimize the operational costs associated with both of these coordinated systems and reduce impacts such as load shedding or unserved natural gas? There's also choices that you can make in terms of coordination strategy. One idea that has happened quite a bit in the sort of academic literature on this is central planning, so being able to operate the two systems simultaneously in an optimized fashion. However, that's not how the systems in the United States actually work. Generally, these are owned by two different companies, and a minimum of two, and in many places in the US, many more than that. And so it's usually more of a market-based system in which each of the two systems, the natural gas system, the power system, optimize for themselves, and sometimes they share a bit of information across that boundary. So we've taken this market-based approach within this at the operational level. Now, finally, there's a number of policy and regulation issues here, And we wanted to examine a couple very interesting ones. There was a few years ago a FERC Order 809, which among other changes required a intraday market for scheduling natural gas deliveries, and so is a policy sort of regulation looking to have better coordination between the power and natural gas systems. And then we also wanted to look at an idea that's called shaped flow. So most gas in the United States is done by what's known as ratable flow. And so that is basically you take the amount of gas that you're going to use over one day and you make that more or less a constant value. You can have a little bit of variation, but not too much. And especially in this changing power system that we'll see later, that's not how the demand for gas actually goes in most locations. Especially if, let's say you have a natural gas turbine that doesn't run that often, it's going to have very peaked requirements for the natural gas fuel. And so it may only run 2 or 3 hours a day. And so we're looking at here shaped flow, which allows the natural gas system to sort of coordinate on an hour by hour basis how the gas demand will change in different locations. And how we've sort of brought this all together is through a co-simulation platform that combines two different commercially available tools. One, SAINT, which is a natural gas dynamic simulation model. So basically what this does is this solves the Navier-Stokes equations for a natural gas system. So it's actually a simulation, not an optimization. I'd like to make that point very clear, just because this is one way in which we differ very significantly from a lot of the academic literature on this, in that that is generally done as an optimization framework, which is not how the natural gas system is currently operated. We do, however, take an optimization-based approach toward minimizing the economic dispatch and unit commitment processes of the power system. And we do this with the Plexo software. So we have 3 different main timeframes that we talk about here. One is the day ahead. So this is very important for the power sector, for large thermal plants that require 24 hours perhaps to start up and shut down. And so in the day ahead unit commitment, you say whether those plants are going to be on or not. You can then in the intraday sort of time period, so this may be 4 to 6 hours ahead of real time, you can then revise some of those for some of those plants, perhaps not a nuclear plant, but perhaps for a combined cycle natural gas plant. And then in the real time, we can then adjust the actual sort of set points of each of those generators. And we do this to try to minimize the operational cost of the power system. What we've done is we've combined this with a gas simulation model so that we can take the demands from the power sector, add them into the gas network, and then ensure that you can actually have a feasible gas flow solution in this case. I'm going to talk here about 3 different sort of results and scenarios that we've run. One is called the power system only. So as you can imagine, this is only simulating the power system. So this assumes basically no coordination between the power system and the natural gas system. How I like to think of this is if we're running the systems isolated, this is what the power system thinks that it can do. Now, that may not actually be true, as we'll see later. We then have the co-simulation approach, which we take the results from the power system demands, we feed that into the gas simulation, and then we can see how the gas network sort of reacts to that. This is what I would say is more like what actually happens. So the power system thinks it can do something, and then the co-simulation says, well, not quite. We may not be able to produce as much power in that one location at this particular time. And so the co-simulation in this case is more of the realistic picture of taking information from both those systems and what might actually be feasible at those times. Finally, we look at the coordination, which is we take the information from the power system, we give it to the gas network says, okay, here are the restrictions, and then we feed that back into the power system so that the power system scheduling can take into account the fuel offtake constraints imposed by the gas network. So this is what it looks like if we have good coordination across those in accordance with the FERC order. Okay. For our case study, we kept it local and we wanted to look at something here in Colorado. And so we worked with our project partner, Kinder Morgan, on this, who provided very graciously the gas network data for Colorado. And we looked at the front range gas network, which you can see sort of a quick diagram of on the right side. So here, not only do you have your supply nodes for the gas network, but you also have compressors, which can adjust the pressure within that network. And then you have the gas generators in different locations, as well as the individual sort of the city gate customers, if you will, so that are supplying the residential and commercial demands for gas. On the left-hand side, we wanted to look at not only the current power system generation mix, which you see there based on 2018 on the inside of that graph. So here in Colorado, as you can see, we have quite a bit of coal generation, quite a bit of natural gas, and then increasing amounts of renewables as well. We also wanted to look at a situation in which we had even more renewables within the system. And so this is based on 2026 fleet data developed by the Western Resource Advocates to try to meet the Excel, which is our local utility here in Colorado, targets. And so what you see is the coal generation decreases. We kept natural gas the same in this case, but wind and solar greatly increase as well. And so you can see in the 2026 case, we have almost 40% of the power being produced by these renewable energy resources, as opposed to the 24% in the 2018 case. Okay, so these are two networks that we'll sort of deal with from now on. Because this is very computationally sort of challenging to do this detailed simulation of both networks and then have coordination going back and forth, iterating between the two, what we chose to do is we chose to simulate only 4 representative weeks. And what we chose there were the 4 weeks with the highest natural gas demand from the power sector. And our reasoning was that these would be the times that would have the most challenging operations between the two systems, because there was the greatest demand from these generators. And so on the left here, you can see just the sort of peak load and the peak net load. So that's load minus renewable generation for each of these different weeks. The weeks with the highest load turned out to be, we chose one from each season. So June 2nd through 8th, July 14th through 20th for the summer, the fall, November 17th through 23rd, and December 12th through 18th. You can also see here on the right, the share of renewable generation as a percentage of load. And so you can see that this increases quite a bit from that 2018 case to the 2026 case, both in terms of the maximum penetration that we see, so maximum instantaneous penetration in the system, and as well as the total energy averaged over that entire week. So we're looking at 2 very different systems here, and we can see that in the results. Just to sort of characterize some of those differences, looking here on the left-hand side about the maximum up and down ramps that we see in net load. So these are ones that gas predominantly would be expected to pick up. We can see that this additional variable renewable energy does increase fairly significantly the maximum up and down ramps that we see in the system, ranging from a low of about 24% down ramp increase in July versus an increase in the up ramping requirements of 95% in the November case. And so one can imagine that this has this increased volatility, if you will, in the power system is going to have an impact on the natural gas system as well. On the right-hand side, we can see the difference here between the ratable flow, what we currently do in most of the power system, and shaped flow. So what you see there is during this period with the ratable flow, you have that constant natural gas demand over the course of each day. And so that is what we're currently doing in a lot of markets. However, for this particular generator, this is more of a peaker natural gas unit. It's only on for a couple hours a day. And so the shaped flow that we see is a much different distribution. And this has some pretty big impacts on the natural gas system, because you have to be able to deliver these sharp spikes of gas rather than a constant sort of level across the entire day. To show how this sort of impacts the power system, I want to walk you through here these dispatch stacks for this Colorado test system in real time. So we're looking at here the 2018 case and the 2026 case. Now, remember that this has gone through the unit commitment process, so the day ahead process, the intraday process, and now this is the sort of final system. In both the 2018 and the 2026 cases on the left-hand side here, in the power system only case, this is what the power system sees, and everything looks great. From the power system perspective, we can meet all of our load. It's no problem. We have, increasing wind and solar penetrations there in the 2026 case, but we think we can handle this variability. When we go to the co-simulation side, we find out, well, maybe the natural gas system can't actually handle what we think it can. And so we see what here we're calling unserved load. Now, I want to be clear that this is unserved load in the simulation is not actual unserved load blackouts, right? Unserved load in this means you're going to have to change your operations. The power system folks would be able to catch this, but they would have to turn on more expensive generators in order to maintain the reliability that we expect. And so that's what we see there in the red on the top. In the co-simulation case, despite the fact that the power system thought everything was okay, it wasn't, because the demands on the natural gas system were such that it wasn't able to deliver gas to some of the generators, and therefore the natural gas generators weren't able to deliver power to the power system. As we move further right to the coordination case, we see that we've been able to greatly reduce that unserved load and thus reduce the cost of operating the power system, as well as reduce the reliability risk to the power system, just by adding an additional sort of feedback loop where the power system can now understand what the limits are in terms of rated flow at each generator in the natural gas network, and then allow the power system to reschedule based on that. So there's enough flexibility in the power system to handle this, but it needs the information that the natural gas system can provide about how much it can actually deliver in different cases. If we look at this now from the natural gas perspective, we can see the demand for generators in green on top, and then on the bottom, we can see the other demands on the natural gas system. So these are more residential and commercial demands, for example. To me, where this really gets interesting is in the November and December cases, when we compare the 2018 cases versus the 2026 cases. The big difference here is we're going from cases on top, where we have quite a bit of natural gas demand from generators, to cases where on the bottom, there are periods where we have no demand for natural gas generations on the system. This is because of the increases in wind and solar power. However, when you look at that as well, that natural gas demand profile is much more volatile in the 2026 case, right? We have these high peaks and these lower valleys that produce some stress for the natural gas system. It's not a constant ratable flow that we can provide all the time. And so this sort of is indicative then of the challenges that we can see in the natural gas system. We have to be able to schedule far enough ahead so that we can provide gas to all these generators that need it. And we're going to be operating the natural gas system much differently than we currently do in a situation like this. The impacts of this then, and we look at this in terms of total unserved load. Again, I want to stress that this doesn't actually mean blackouts, right? This just means corrective action would need to be taken that would be very expensive in order to maintain power system reliability. So as we progress from the sort of left to right here, you'll see in all these cases, with the minor exception of July, the power system thinks it's fine. There's no issue. It has all the generation it needs. In that co-simulation case, we can see that there's quite a bit of unserved load. So this really is indicating that the power system doesn't have as much flexibility with those natural gas generation as it thinks it does because of the constraints of the natural gas system. However, when we go to the coordination case where we provide that information to the power system and we allow it to re-optimize, we eliminate almost all of those troubling periods. And so this is a key sort of aspect in that what the FERC order can do is allow for this better coordination and information sharing between the two large infrastructure systems that will allow for more efficient utilization of all the resources that are in both. When we dig down into this a little bit more, we can see that in this Colorado test system, the majority of this unserved gas offtakes, so these are times when generators can't get all of the gas that they want to generate, comes from 2 nodes within the system, really. And we can see specifically not only that it's this node 29 and node 31 where we see a lot of this, but that coordination reduces those. But we also see who picks up the slack, if you will. There's a little bit more taken by node 26, which is upstream in the system, and so that's available. But then also downstream, we're able to deliver a little bit more gas that wouldn't be able to be delivered in these particular locations. Okay, and so as we look once again just at the sort of summary of all those coordinations between the two, on the left-hand side, we have here the total unserved natural gas per week. So looking at this from the natural gas perspective, this mirrors that of the power system perspective. In the co-simulation case, we have lots of unserved gas in many of these cases. However, when we do the coordination between the two networks, we can dramatically reduce these by allowing the power system to utilize other assets instead to produce this power. So this redispatch of the power system based on the natural gas system constraints can reduce the unserved gas by about 97% relative to the co-simulation. Now, I do want to stress that these are probably the most stressful 4 weeks during the from the power system and gas perspective. And so, you know, there may be weeks where you don't see any of this difference, but these are the periods that we're worried about for reliability purposes. On the right-hand side, we see then the difference in ratable versus shaped flow. So allowing the natural gas generators to nominate not on a daily basis, but on an hourly basis reduces the amount of unserved gas, even in the sort of more simple cases in 2018 and 2026. But then allowing coordination as well can dramatically help to reduce the amount of unserved gas that we see. Now, this is very important. Again, just to stress, in the US, we have residential and commercial loads, which are basically guaranteed contracts, guaranteed delivery, whereas the generators, the natural gas generators in the system, generally have breakable contracts where they don't always have to have delivery. And so that's the difference that we see here in this coordination, is the natural gas system prioritizing the delivery to those guaranteed contracts and then being able to have unserved gas at some of those natural gas generators. So this shape flow can dramatically reduce, especially as we go to higher amounts of variability in the net load of the power system, the amount of gas offtakes that have to be curtailed compared to a ratable gas nomination. To summarize, we're really excited about this work that we've done on the interface between the natural gas and power systems, which are increasingly having impacts on each other, not only economic, but also in terms of reliability. And we found that coordination between these networks can greatly reduce the amount of curtailed generation. So this is possible to have reliability benefits as well as reducing the amount of cost increases we see from instances like this. On the other side, the coordinated intraday markets, similar to what's proposed in the FERC order, can reduce unserved natural gas by almost 97% in this Colorado case study, which is pretty amazing. The different factors that drive these demands for gas and perhaps the shortages of it are only expected to increase as we increase more variability and uncertainty on the power system with increasing wind and solar. And so this is going to become even more important. There are ways that we can deal with this in the natural gas system, whether that's just through line pack, whether it's through compressors, However, we need to be able to share information across those more accurately in order to take the best actions. Finally, moving from constant daily flow, so ratable flow, to hourly nominations or shaped flow can also play a great part in reducing the curtailed gas offtakes, particularly when we're looking at increased penetrations of renewable generation. So with that, I'd like to thank you very much, and I'd be happy to answer any questions.
Thank you, Bri. We do have a question about curtailment. So has the curtailment become less when you changed from co-stimulation to the coordination case of these systems?
Yes, thank you very much. So I assume we're talking about curtailment of renewable generators, and the answer is yes, there is some decrease in the curtailment of renewable generators during these periods. I would say it's not dramatic differences, but there are differences.
Okay, great. And it sounds like that'll be in the publication, probably more information about that. So next question is, does your study take into account the role of natural gas storage?
Yes, thank you very much. Great question. So we do have natural gas storage within this system, as is currently available in the Colorado test system. One of the things that we're looking at as a sensitivity that will be in the final report is increasing the amount of storage for natural gas at generator locations, as well as on the system, so that we can understand the impacts that natural gas storage, as well as additional electricity storage, would have on these results.
Great. And one more question. Did you incorporate natural gas constraints as much as you could in the unit commitment, or was the unit commitment model totally blind to these constraints? And it would be interesting to see how adding these constraints would improve the results. So how did you work with the natural gas constraints in the unit commitment model?
So the original unit commitment model, so the power system only, does not have delivery constraints, as these typically aren't reflected there. Where they are reflected is in that sort of iterative process where we go back through. So the coordination case then reflects those constraints.
Okay, excellent. Thank you very much. So it's time to go on to our next presentation, which is on renewable energy in mining. So this is part of our next theme, which is around industry and agriculture. And we'll start with a presentation on mining, and then we'll move on to LED lighting and the energy water nexus. So I will turn it over to Travis Lowder and also collaborator JISEA Agogo on what we're doing around renewable energy and the mining sector. Travis?
Thank you, Joe. Oh, sorry. Thank you. Hello, everyone, again. I will not spend too much time on my bio here, as I spoke earlier, but just as a reminder, my name is Travis Lowder. Background in renewable energy policy, finance, regulatory matters. I have been working with Jill and JISEA Agogo, who has been my collaborator in this process, but will not be speaking today, on a project to engage the mining industry on similar to an analytic suite of services that we might be able to provide them that we saw in the last presentation with Bri-Mathias. We held a workshop in November that pulled together over 30 professionals from the mining industry, suppliers to the mining industry, trade associations, other stakeholders. It was generally to discuss opportunities and barriers to incorporating more renewables into mining operations. And from this workshop, we have assembled a sort of laundry list of things that we believe could be helpful in having the mining industry access renewables at scale. And TC is also currently working on a paper that should be out maybe in the next month or two that sort of lays out the issues We encourage you to look forward to the publication of that. The following presentation is going to be based on the learnings that we had from this workshop, as well as some of the research conducted by TC for this paper. So to kick things off here, excuse me, this is a graphic from our friends at the Columbia Center for Sustainable Investment. They did a report on renewable energy and mining that was fairly comprehensive and well done. That is publicly available, so I encourage you to also seek that one out. But I'm going to use one of their principal graphics here to sort of lay out what the macro issues are. So the mining sector is anticipated to only increase its demand for energy in the next 10, 15 years here as demand for minerals ramps up. A lot of the minerals in our electronics and certainly in the renewable energy technologies that we're using more of are in high demand, and that demand is anticipated to grow. And falling ore grades are also making it such that you are having more energy input into the extraction of the same amount of minerals. The expense of that energy is also climbing. It's anticipated that energy expenses today are about 15 to 40% of total operating costs. And as fuel prices and electricity costs continue sort of their upward tick over time, we anticipate that these costs could take on a larger share of mining operations. For some global context, currently about 11% of energy use worldwide is attributed to the mining industry, both for the extraction and processing parts of their value chains. So you've got rising energy costs. Energy, for the most part, is supplied by fossil fuels in the mining industry. Even electric loads are heavily supplied by fossil fuels. We're talking principally diesel and heavy fuel oil for on-site loads, but in places where mines are drawing off the grid, obviously that power is coming from coal and natural gas in a lot of cases. Fossil fuel volatility is a high concern. Mines operate in a lot of different environments, but remote environments and off-grid environments happens to be a place where they tend to have a cluster of activity, and with disruptions to the fossil fuel supply chain that can disrupt operations, then it can raise costs. And of course, with fossil fuels, heavy fossil fuel use comes rising greenhouse gas emissions. This is not only, as I mentioned in the previous presentation, something that's companies are looking at from a good citizenship standpoint, but there's also regulations that many are anticipating coming down the pike that will put a price on carbon. And then there's also the issue of local communities. So this is an environmental societal governance thing and a shareholder value thing, which dovetails into this social license to operate icon there. Social license to operate essentially being, can you get the permission you need from the local communities in which you want to run an extraction operation to run your operation, essentially. Issues with local air and water pollution and other things have sort of given the mining industry a bad rap over time, and mining industry is looking for ways to improve their relationships with communities, give back to communities. Renewable energy can certainly be one way to do that. And then I'll just go to this last icon there on competitive advantage, talking about the source of minerals. There may be market advantages to companies that can demonstrate that they extract their resources cleanly, and there may be market advantage for products that can demonstrate that they are using resources that have been extracted by or produced by clean energy. This is something that becomes quite challenging. We won't get into the details on this today, but this is certainly something the mining industry is looking at and several have implemented pilots, for example, using blockchain to track their minerals through the supply chains. This slide sort of just doubles down on what I just said, but it ranks the risks. This is a Ernst & Young report. The mining industry is facing a number of risks going into the third decade here. Excuse me, yes, third decade of the 21st century. This is a ranking for 2020 from Ernst & Young, and you can see here that social license to operate and reducing carbon footprint are within the top 5, and renewable energy is certainly a technology and a solution that could help address these two things. Other risks, such as rising costs, could be addressed with renewable energy as well, certainly as a fuel hedge. So this risk stack is really just to show that the things that are keeping the mining industry CEOs up at night, renewable energy could be one possible pathway to help mitigating some of these risks. Lastly, just for context, I will talk really quickly about circular economies. We are all sort of heightened in our awareness of supply chains these days, seeing the shortage of masks and ventilators out there to help combat the spread of the COVID virus and help those who are infected by COVID or coronavirus and infected by the coronavirus. So supply chain is very important. Many of the materials that go into renewable energy technologies, steel and batteries, you've got nickel and cobalt and lithium and things like that. These are highly important to the renewable energy industry. And so this is something that we particularly and others are excited about, sort of bending these two supply chains to meet and linking them in such a way that you can uncover efficiencies. So that's an opportunity. It's something we haven't necessarily quantified, but it's something certainly to keep in mind. And we hope to do more work on this as we move forward with our mining work through JISEA. So given this context of the mining industry's risks and of course the global energy and emissions risks, renewable energy has at least some benefits that it could provide to address these challenges for the mining industry. Over time, we're all familiar with these curves, and I'm not going to sort of dwell on the numbers here, but we know that renewable energy technology costs have been falling, certainly over the last decade, but these costs are anticipated to decline even further, particularly for technologies such as batteries. These are cost projections that NREL has put out for batteries going into 2050. And if these costs continue to decline and the technologies continue to improve, it only makes more sense, both economically and from a risk reduction standpoint and a social license to operate standpoint, for mines to look at these technologies. And they have been. So this chart shows the number of renewable energy projects that have been installed or announced over the last 2 decades. And we see here that just within the last year, we've seen a massive uptick of renewable energy project announcements or installations. Since 2015, really, this has been sort of the hockey stick moment. Falling costs and rising awareness are driving this, but I think the mining industry is also figuring out how to incorporate these technologies into their operations. So, so the trend is moving upward at an exponential rate currently. So there's lots of opportunity to fine-tune things and really bring these technologies in at a higher level. Moving on to mine-specific activities. So every mine is different, operationally speaking, but also, you know, in terms of how they are extracting the minerals, what minerals they are extracting, where they're operating, etc. So this is a sort of a comprehensive view of what a mining site might have in terms of energy loads. I'm not going to read through this list. Obviously, there's a lot here, but I'll sort of draw your attention to the fuel source column. And you'll notice that electricity and diesel or fossil fuels, and where we say fossil fuels, we might mean primarily natural gas, is driving the bulk of loads on site, both for extraction and for processing. So there's a lot of opportunity here to do a switching for generation sources. So, if you've got electricity loads, you can swap in a renewable energy project either on site, or you can do some kind of virtual PPA arrangement or community arrangement. But there's also opportunities to electrify loads on site through batteries powering the haulage trucks, et cetera. We'll talk a little bit more about that in a minute. But just to sort of reiterate what I said previous, with all the differences in mine operations, electricity is the largest energy demand. This chart here on the left gives you a look of sub-Saharan African mines, just sort of as a cross section of the industry. And you'll notice here that with many of the loads, fossil fuels comprise the bulk of what they are relying on to supply these loads. So renewable energy is sort of ready-made to step in to supply some of these loads, but there will be some challenges to do so for loads that maybe aren't electric, or also supplying mines with more energy than, or with higher amounts of, well, sorry, I'm getting ahead of myself. I will wait for the next slide to talk about that. But renewable energy applications in mining, as I mentioned, there's a huge opportunity for renewable energy projects to step in now and supply the on-site electrical loads. I also mentioned the replacement or electrification of diesel-fired loads. You see that truck there running on those cables. That's one way to do it. Hydrogen is another way to power these large haulage trucks or on-site transportation. We are seeing both of these technologies, electrified battery-powered mobility as well as hydrogen mobility. These projects are being piloted on mine sites currently. And renewable energy on-site electricity provisions are happening all over the place too, as we showed you in that chart earlier with the hockey stick for project installations. More difficult for the renewable energy industry at this time to sort of serve the mining industry is in areas like process heat and feedstock substitution. These technologies are perhaps a little less mature, and more R&D is going to be needed to drive these further. But that is also work that is happening not only in the mining industry, but across heavy industry and tire. So we're talking cement and steel manufacture, et cetera. So gains in one industry can certainly be used to drive innovations in the mining industry and across industries in general. Some of the barriers that we have heard from the mining industry and that we have uncovered in our research to incorporating more renewables. Number one is the variability of renewable generation. And I've got a couple slides after this to illustrate that. But certainly when you've got constant loads and generation that's variable, and storage is still a technology that might be out of the money in terms of economics, or not provide you with the duration of storage you might need. This can be something that's that the mining operators are finding a challenge in incorporating more renewables. So it's not an easy one-to-one swap. You have to sort of account for the variability. Another thing that we heard, this was a big deal in the meeting that we had in November, conflicting business models between the mine operators and renewable energy developers. This is largely in the contracting. In renewable energy contracts, you have these take-or-pay provisions, which essentially the renewable energy developer has to earn its return on its investment. So they have to have some guarantee of cash flow, which means that they have to have some guarantee of purchase. And whatever energy is produced has to go to the off-taker. in this case being the mining operator. But the mining operator, this is going to reduce their flexibility to operate. Changes in the market for the commodity price of a certain mineral or what have you could change the operational parameters on site. And this flexibility to sort of change given market context is or change operations and therefore change loads can be sort of antithetical to a contract that obligates you to pay for every kilowatt hour that's generated by a renewable energy system. So there are opportunities to sort of improve these contract structures, but this was brought up as something that the mining industry is certainly thinking of and experiencing some difficulty with. There's a lot of renewable energy expertise that's lacking in the mining industry currently. We're seeing a lot more of it, certainly with all these project announcements and installations. But right now, one of the big things we uncovered in this workshop that we held was that education for mining engineers does not incorporate renewable energy currently. So when these engineers go into the private sector, they start working for consultancies or they're on staff with the mining companies. They don't have the tools, the expertise, the experience, et cetera, to evaluate renewable energy technologies when they're doing their mine feasibility. And this can be problematic because there's no sort of from the cradle consideration of renewable energy technologies. There's a lot of bolt-on for mining operations currently. So considering these things from the start can certainly help to sort of drive the uptake of renewable energy technologies in the mining industry. Other barriers include land constraints. There's a lot of mine sites that do not have the sites or the available parcels to install these technologies, certainly not at the scale that they might need for their large operations. We're talking 20+ megawatt operations. There are options for this, green sleeving, et cetera, or virtual PPAs, although that's going to depend on market and regulations. And then there's technology readiness and R&D gaps. These are related mainly to the things that I mentioned about feedstock substitution and process heat demand. But there's also issues with variability and the maturation of storage technologies. So real quickly, just to give you a snapshot about the variability piece, because this is one of the largest challenges. These are actual load curves and generation curves from a mine site. I won't say where, but you get the sense here that the wind generation is it's oversized relative to load to sort of give you they've got storage on site as well. So a lot of the over generation will go to storage, but that's an economic consideration, and as we'll see on the next slide. But many of the loads or generation spikes are way over the load of this mine site, which is the green line there. And as you can also see, the generation curve will also drop well below the load curve, sometimes for a matter of days. So this is highly challenging. You've got either more energy than you need or less. So storage becomes essential. But with storage, this is an analysis done by a gentleman by the name of Joel Guibault. He's an employee of Hatch, which is an engineering company that serves the mining industry. And he did this levelized cost of energy analysis to evaluate when technologies that have storage make sense, at what level of renewable penetration. So you can see here, I won't go into this, it's kind of complicated, but there's a sweet spot for certain technology stacks with storage or certain technology penetration levels with storage. And it's going to depend on site, and it's going to depend on the technology stack and the duration of storage you have. But at a certain point, renewable energy penetration, and it's right around that sort of 60% mark there, it starts to go upward. At a certain point, renewable energy penetration doesn't make economic sense for the mining industry, even with certain levels of storage that can last through the long troughs that might happen from the variable generation. So this is a challenge to getting more renewables on site for the mining industry, but it's one that right now there's no sort of silver bullet solution. I know of a mine site that's got hydrogen storage, it's got lithium ion storage, and it's got hybrid plants, both in solar and wind. And they're trying to optimize between those various technologies and those various storage technologies to run their mine. And right now, the economics pencil for them, but again, it's very location specific. And this is where expertise certainly comes into play, having the ability to evaluate what technology stacks and storage durations make the most sense. So in terms of solutions to some of the barriers we discussed, certainly where the business model misalignment exists between renewable energy developers and the mining industry, there's opportunity to engage both those industries, bring them to the table, discuss ways to have their interests represented in contract structures mutually, and come to some agreement about what's acceptable and what's not, and you know, what you can contract for and who bears what risk. So this is something that NREL through JISEA is looking at doing through this working group. We're also looking into capacity building. This includes trying to drive educational programs or mining education programs to include more renewable considerations, but it also includes capacity building at mine companies, governments, so that they can regulate and evaluate these projects with renewables and maybe help to drive renewable policies that could facilitate more incorporation on mine sites. Technology development and critical path R&D. This applies to the things like growing the renewable penetrations on site, also feedstock substitution and process heat. Supply chain certifications, we spoke about this earlier. Some companies are piloting these blockchain platforms to track minerals through the value chain, but it can be very difficult if these companies that are doing the extraction don't have processing facilities and they release their minerals onto the market. That's certainly a big challenge, but one that we can incrementally address, certainly through the companies that have the greater control of their supply chain. Policy and regulatory measures, and collaboration. And on that note, we are looking for participants in this JISEA working group. This workshop that we held in November was sort of the kickoff to this whole thing. We incorporated the feedback, and we've sketched out this program that includes narrowing down on the best practices, developing these model contract structures, et cetera, to align business incentives, technology analysis, you know, what technologies work where, what kind of penetrations can you achieve, what's the economic optimum for these technologies, and what's the sweet spot. Strategy development, what are the regulatory, economic, societal, et cetera, trends coming down the pike that will affect operations in the future, and how can you plan for those things now, and other analytic aspects that any sponsors would choose to bring in. So if you are interested in joining this group, please reach out to me. My email is at the bottom there, and on this slide as well. That is it for this presentation. I will just remind you that TC has been working on this paper that should be published in the next month or two. So please access that paper when it comes out, and we'd love to stay in touch with you on this topic. Thank you.
Great, thank you very much, Travis. And yes, if people are interested in this paper, you can sign up for the JISEA mailing list, or you can follow us on our social media sites. We will post it when it is available. So we have several questions. The first one it came in during your early part of the presentation, which, because I think you mentioned a number. What is the percentage of energy used for mining worldwide, if you know some of those numbers?
Sure, and a lot of this will be in the paper, but the figure that I was pulling from the paper was 11%. I'd have to go back in and check the source and everything, but that's the one I believe we've cited.
Okay, great, thank you. And do you know Can you talk a little bit about the differences of mines that are off-grid and on-grid? And do you know the share of off-grid versus on-grid, or if not, kind of talk a little bit about what the differences between those mines are?
Sure, and I will just sort of preface this answer by saying there's lots of ways to slice and dice mines. You can do it by the mineral they're extracting. You can do it, is it above ground or below ground? Is it off-grid, on-grid, et cetera? So this is one way to look at, and you would do that sort of to evaluate, what's the tailored solution in terms of a renewable energy. So for off-grid versus on-grid, certainly if you're on-grid, then you're working with a reliable stream of electricity. When I say reliable, you could be in a country where blackouts are a common thing. So maybe your grid connection really isn't that reliable. But in the United States, you have a lot of on-grid mines. I'm not going to be able to give you any percentages of split between on-grid versus off-grid. But when you've got that reliable supply, that can be a backstop to the grid. And then there also might be some net metering capabilities. A lot of state laws will cap net metering at levels probably below what you would want for a mine site, but there might be some way to take advantage of the regulations through a bilateral situation or special regulatory provision. And you can feed that energy back onto the grid. So essentially you're using the grid as a battery. So that's one way you could look at an on-grid site. An off-grid site, you're going to have more storage, obviously, and that storage can come in the form of lithium-ion battery, hydrogen, or it can be diesel storage on site, and diesel provides your backup reliability. There's a lot of different ways to do it. I think principally when we talk on-grid versus off-grid, it's really just how it's sort of configuring that reliability, making sure that you have the backup power you need, and then figuring out what technologies and what fuel sources will provide that. There is a mine in Africa somewhere. I don't remember what country it's in, but I heard about this recently at a conference. It's a B2 gold mine, and their storage capacity, they've got a massive solar field. I think it's somewhere on the order of 20 megawatts or 15 megawatts or something. And they've got a storage facility, lithium ion, that's a quarter of an hour. It's very quick. But that quarter of an hour makes economic sense because it allows them to ride through any hiccups. They're an off-grid mine, but they can ride through any hiccups and reduce diesel usage and also prepare for diesel usage when they have to. So they're not just sort of quickly toggling back and forth between their diesel gen sets and their solar field. They've got sort of a glide path with this battery. It's made a lot of economic sense for them because the cost of providing power to that facility, being an off-grid facility, was very high. So not sure that sort of directly addresses the question, but those are some of the considerations that would go in to evaluating off-grid versus on-grid from a renewable energy perspective.
Yeah, that's great. Thank you. Real quick, there was a question about oil and gas extraction is also incorporating renewable energy. Do you see there's parallels with that industry, or is it pretty significantly different in how renewable energy can be incorporated?
Jill, I might kick that back to you because JISEA has oil and gas projects, and while I think there's some high-level similarities for certain, I'm not so sure, specifically if that comparison holds up. Do you have thoughts on that?
Yeah, I'll mention that real briefly. We are doing a renewable energy for oil and gas extraction project, oil and gas operations, which is essentially, an extractive process. There are similarities, but there are also quite a few differences. The oil and gas operations tend to be more decentralized, and they can be both grid and not grid connected, but they are a little bit different in terms of they're not the very large mine sites that you see with mining. So there's definitely parallels. I think some of the models we're developing for that industry will be applicable to the mining industry, but the load input will be pretty significantly different. But do look for those reports. We'll be having some of those results come out as well. So it is time to go to our next presentation. Thank you very much, Travis. And our next presentation is focused on our work around supply chains, and this is getting into energy efficiency. So I'm going to turn it over to Samantha Reese, who's going to talk about LED lighting and how that looks globally and where we get all these wonderful lights from these days. So Samantha?
Thanks, Jill. All right, one of my favorite topics, solid state lighting using LEDs. We did a project that started in 2015 and wrapped up in 2017. So I want to preface it that a lot of the data I'm showing on LEDs was from that time range. And so we realized that it is a rapidly evolving field and there has been a lot of changes of who the main players are. So just to preface that right up front. So really our goal was to provide objective supply chain analysis to kind of inform some of the research investment in the development of lighting. The Department of Energy Solid State Lighting Program has been investing for the last decade in LED research. However, there was this perception that given that all the dye are not manufactured domestically, how is that benefiting us? And so, our analysis was looking at the trade of the components to understand how various regions play a part in the overall supply chain, quantifying the current capacity and production to understand who is currently supplying and who would have the ability to ramp as adoption becomes more widespread. So if something changed tomorrow, how fast could the manufacturing ramp up? Which regions would be providing it? And we try to provide market data to put the research problem in context and help analytically show that technology potential. So for this project, we really focused on an integrated luminaire. For those of you who don't know what a luminaire is, you're in good company. When I first started, I was like, what's the luminaire? It's basically the entire fixture with the light generating device. Now, in previous technologies, the fixture would come and then you'd buy your bulbs and you'd put your bulbs. But now with solid state lighting, you have these LEDs integrated within the light. There is no thought that you're going to change out something later on or the bulb will burn out. And so an integrated luminaire has the LEDs built into it. It has the drivers or the necessary power electronics, and then it has the frame and the light diffuser and all those pieces. For the project, we used a 2x2 troffer as an example. Troffer is essentially a commercial light. It's what you would oftentimes refer to as shop light, or when you used to get to go to your office building, it's the types of lights you frequently see up there, especially in open space concepts. And so what we're really trying to do is understand how could the R&D investments in the product not manufactured domestically actually benefit the domestic economy. But what is the motivation for solid state lighting? The Department of Energy solid state lighting program conservatively estimated that the LED lighting sales were going to increase from being about 3% in 2013 to 48% this year to 88% in 2035. And if you think about if you ever go to, or when you get to go back to a hardware store and you look around, what you really notice is that your lighting options have significantly changed and that this is a conservative estimate. And so it's probably even higher than that, that when people are buying lights or doing retrofits now, more and more they're using solid state lighting based products over the CFLs of the previous technology generation. They figured that if the acceptance rate matched their estimates, that it would result in 251 terawatt hours in site electricity savings annually. I was like, okay, so what does 261 terawatt hours actually mean? Because it's always really hard with like you hear a number, you're like, okay, that sounds like a lot. That would basically be about 60 times more power than Cooper Jam generates. So they're estimating that if all this was to happen, we would have 60 Hoover Dams worth of power conservation. They further figured that if they were a little less conservative and all their priorities and milestones that they laid out in their roadmaps were achieved, that you'd actually get an even higher increase of 75%. Of interest, so LEDs have been around since the early 80s. They were actually invented in the US, and then Taiwan started to do a lot of research and development. Early LEDs were just indicator lights that you would see in you'd see in electronics, and then you started to then have more adoption of LED monitors, TVs, you see in the cell phones. However, starting in 2014, over 50% of LED revenue was actually being generated by lighting products. So to kind of break this down, though, in the different markets, you have LED lighting that goes into residential, you have it commercial, industrial, and outdoor. So more lights are used in residential settings. However, the estimate is that a residential light is only on for maybe 3 hours a day. So even though the vast majority of the widgets are in the residential, the amount of energy use is only about the quarter of the total used for lighting. In commercial, you have a lot less commercial lights. However, they're on all day. When we would go to an office, so those offices are typically open at least 6 to 6. And so they were actually using 50% of the energy consumed by lighting products. In industrial, there's very little industrial lighting. They use very specialized lights. Industrial lights are going to be harder to replace with solid-state lighting due to the harsh service conditions, and they only use about 8%. One of the areas that actually, and again, as you kind of look around and you see, is outdoor use. So street lights, highway lights. There's actually a remarkable few number of those lights, but they actually use an enormous amount of energy due to the need for them to produce high quality light that is disperses over a wide area. But for the purpose of this project, since we were really focused on manufacturing, that's why we decided to go with looking at a troffer. Is even though because that is where you have a nice combination of the amount of manufacturing coupled with the amount of energy use. And so kind of your biggest bang for the buck. Kind of give an idea of the areas we touched in on this project. We treated the wafers as a buy, so we just used market reports to figure out what their average price to purchase would be. But then we really focused on the manufacturing of an LED chip as a package, and then the ultimate luminaire. So basically, your process for an LED-based luminaire begins with LED manufacturing, which is consisting of growing the LED wafer, with the growth of the LED on the wafer by metal organic chemical vapor deposition. You then process the LED wafer by a conventional semiconductor process. You separate it into individual LED chips. The next step is you put those chips into LED packages. Depending on what that package will be used for, you will use anywhere from 1 to upwards of like 8 chips. And then you deposit phosphor materials. So in order to get the white light that we're all looking for in a lighting application, you're putting down a phosphor to help select the appropriate wavelength. And then finally, you put those LED packages into the luminaire, integrating it with a driver, a heat sink, and all the necessary optical components. And then you have a new LED light in your house. All right, let's start with the global supply chain. Where is stuff coming from? So one of the things you're going to notice that in 2015, when you're looking at the raw materials necessary, you're not going to find a whole lot of it in the United States. All the main rare earth elements are being processed over in China. So that's the indium, yttrium, uranium, gallium. These are all the precursors and stuff necessary for the phosphorus down selecting. Then we started looking at, as we take a step back of where I was showing you the value chain of what we looked at. We looked at where the wafer is coming from, then where are the die made, the packages, and whatnot. And you can see that the vast majority of the wafers were being manufactured in Taiwan, Japan, South Korea, and a little bit in China, and the U.S. had a very little tiny bit there. Most of those were being done by Cree. Then in the manufacturing of the LED die, which is shown here in the kind of the light blue color, you see that the U.S. is manufacturing a little bit more, but again, the vast majority of them are being produced in China, Korea, Japan, Taiwan. I do want to say a little bit about die. Not every LED chip is the same. You can have quite a large quality difference and quite a large difference in the amount of light generated. And so one of the things that we did find over the course of the project is while the U.S. Manufactured very few die, the ones we did tended to be of a higher value since they were used for larger light outputs. And so you see them more in things like that single LED you have in your cell phone. Finally, the LED packages. LED packages do not require that specialized of equipment, and so it's typically done by contract manufacturing. And so in this one, you start to see that Malaysia plays a piece in the puzzle. One of the things that we were really interested in was understanding what is the current capacity and production of the site. So what does this really mean, like moving forward, if the lighting is actually going to start getting adopted? In 2015, you can see that South Korea, Japan, Taiwan, China, once again, had the vast majority of the substate market. However, it turns out that there had been a lot of capacity expansion from about 2010 to 2015, so capacity utilization was pretty low. And so while Japan was almost fully utilizing their abilities to ramp, China at the time had quite a lot of growth potential. And sitting now in 2020, after a little bit of industry consolidation, because there was such an overcapacity, China is now a more dominant player than either Taiwan or Japan. The next piece, as I described, is one of the things we really look at is what are the trade flows. And so when you look at an integrated luminaire, you kind of have a couple main components. You have your LED dies in it, and then the packages that they go into. And the other big thing that you have is this chunk of steel in order to make the frame of the luminaire. So we looked and figured out where is the steel coming from. And our conclusion was that basically steel is globally traded. There's not really any single dominant source. And so that there was no reason to assume that any of the steel used in a luminaire was coming anywhere else but from whatever economy it was being manufactured in. Then the next piece we looked at were the trade flow of the dies and the packages. Now, as I described before, you can make your die in a different place than you make your packages. However, in the trade flow codes, they don't actually separate these. So I will caveat this data that it is both the die and the package integrated. One of the big things we noticed is there's actually considerable trade between countries that we knew didn't actually produce either die or packages. We actually adjusted the data to compensate for that because it could actually make things look like more product was produced than actually occurred. It looked like it was being more used as intermediary countries to pass products through for whatever favorable trade or tariff reasons there might would be. Here you can see that the U.S. actually did $1.9 billion of export in die and packages. Again, going back to not all LED, any given LED is not the same. And so even though the U.S. had a much smaller percentage of manufacturing, their higher quality, higher value meant that it still was a $2 billion industry in 2015. We next was looking at the trade flow of all the luminaires. So where are all the lighting products coming from and to? The trade codes were not really sophisticated enough to differentiate whether a light was an LED light or a traditional light. So these are all grumbled together. What we found is that China, in fact, dominated the trade of the luminaires. The U.S. in 2015 imported 3.9 billion, with the vast majority of that coming from China. However, we then looked at what is the actual lighting market in the U.S. And according to a Navigant Research market report, the market was $17.3 billion. So if the U.S. imported 3.9 billion, therefore we actually domestically manufactured 13 billion in lighting products. So 77% of the total revenue of lighting products sold in 2015 was manufactured domestically. So any innovations in LED technology is incentivizing further, even though we ourselves here may not actually manufacture that specific LED chip, it is incentivizing us to manufacture the LED luminaires. The next part that we tackled was doing some bottoms-up cost modeling to understand, well, then how does this affect each of the different the market? So where is the value add in this chain? Looking at it now from starting at the LED die, package, and luminaire. So bottoms-up modeling. So our models really take into account the core country factors, things such as the labor rate, electricity prices, effective corporate tax rates. One of the things we did do is we assumed the same knowledge capability of the firms of each country, trying to kind of have an apple-to-apple comparison. We assume all equipment is fully purchased new, and each of the companies is having to pay for it in the same way. Now, we know this is not true. For instance, in the solar industry, we know that there was a lot of subsidizing of the litho tools for PV panels. However, again, our purpose here was really to do an apples-to-apples comparison of how does any given economy compete in figuring out where the value add would be. We assumed the same production volume, yields, and diameter of wafers. We also assumed that especially in areas where the capital equipment was a significant portion of the manufacturing cost, that there was full utilization, no subsidies. And what we modeled to was the minimum sustainable price a company was going to have to sell the product for in that economy in order to pay back the capital operating expenses during the plant lifetime. And what we found was that if you look at the value chain of an integrated luminaire, that the chip accounted for only about 5% of the value. When you then took the packages necessary for that 2x2 troffer that I said we were using as our example, which has 80 chips in it per light, then that's about 30%. And then which meant that there was 70% of the overall value was actually coming in the form of the luminaire when you looked at what the average selling price was going to be. So when you consider that lighting market was $17.3 billion, we imported 3.9, then of $13 billion in lighting products, we were manufacturing the highest value add of along that entire supply chain. So kind of using each of these, the various economies as we modeled, we looked at how much would they have to be selling that 2x2 troffer. Now, again, I want to really emphasize, we were modeling the price that they would have to sell it for to pay back, given those assumptions. This has nothing to do with when you walk into Home Depot or your local Lowe's and you look at the cost that you would pay, what it would be. Because oftentimes the market has other factors at force, and so so we basically modeled to figure out, okay, yes, if you manufactured a 2x2 troffer in China, it was going to be able to be sold for a significantly lower price than, for instance, one manufactured in the U.S. But you have to get it to where you want to use it. And shipping's not free. And we're not talking about when we're looking at like a die, you could put 1 million die in a box and put that box on an airplane, and your shipping is going to be inconsequential. A 2x2 troffer weighs around 18 pounds, and so you can basically fit about 408 of them in a 40-foot shipping container. And so then we looked to estimate how much would it cost to get it to Golden, Colorado. because why not Golden, Colorado? We assumed that you magically would be able to get these troughters to a port so that we weren't accounting for any costs associated from a factory, for instance, in inland China having to go out to Shanghai to get it to the port. So we said from the point that trougher magically is sitting on a ship wherever it was manufactured, and that then it reaches Golden, Colorado, how much is this going to cost? And for the U.S., we were figuring that it was manufactured in Texas, because we had anecdotal data from attending some conferences that that was where one of the bigger trougher manufacturing locations were. And so you can see in the bright green the cost to actually get the product here. And so if you look here in the blue colored bars, you can see the cost difference compared to the U.S. to manufacture and ship the product for it to reach Colorado. So you can see it would cost 30% more to manufacture a 2x2 trougher in Germany than it would if you were to purchase one that was manufactured here in the U.S. Now, it still is about 4% less cost to get a trougher manufactured in China. However, the purple bars indicate the minimum time to reach Golden. And again, this is assuming like that ship is just sitting there, it's just waiting to do nothing more than move your product, and that when you reach the U.S., that the port just has a slip available and you just slide on in. Again, research shows that this is not true. There is often a lot of different delays, and that ships can actually be waiting quite some time for both loading and unloading. But we were really going on the conservative, what is the minimum amount of time it would take you to get from one place to another? And for instance, it's going to take you almost 20 days to get here from China. It's going to take you over 50 days to get here from India. And one of the big takeaways from attending lighting conferences, listening to the integrators, is that the lighting world is a rapidly evolving world, and that the products are changing so fast that waiting 2 months in order to get your product in that amount of time, you could have had significant changes, and it already can be obsolete. I think this is starting to slow down, but at least at the time, this was really kind of the overall message that we were hearing. So, in conclusion, general lighting is projected to consume 70% of the packaged LEDs manufactured this year. Advances in LED technology incentivize luminaire updates. So all that R&D money that is being invested make the LEDs both more energy efficient and more appealing for a consumer, incentivizing people to want to do retrofits and to use the product in their new builds. It's rapidly evolving, so things that involve the long shipping times are really undesirable. Having a 4% cost savings, but waiting upwards of a month to get your product when you're on a timeline and there could be further delays is just one of the things we really heard is just not worthwhile. So the cumulative result is that LED integrated luminaires reduce energy needed for lighting and have a value chain that allows for domestic manufacturing, benefiting a domestic economy. So there's really no reason to think that this is only would hold true in the U.S. For instance, buying a light in Germany that was manufactured in Germany is going to have the same benefit. All right. Questions?
All right, thank you very much, Samantha. We have a couple questions. The first one is, does the cost analysis address the maintenance cost offsets associated with changing lamps within a commercial facility based on the luminaire's life cycle? Or if not, do you have any thoughts on what kind of the downstream maintenance and operation might be around these new type of lighting?
So the cost analysis does not take any of that into account. This is straight up if you were to purchase a new luminaire. One of my thoughts on LED lighting is I think it had initially a really rough rollout. I think there was a lot of hurdles that had to be overcome there was a lot of problems where there was some driver issues and whatnot. And I think they've actually solved all those. And so now with an LED light, instead of having to like change out bulbs, and I forget what the frequency is, but I think it's like every 18 months or something. Now you don't need to do that. So I think for the next step is really of the value, and there are some tools out there produced again by the Solid State Lighting Program that will tell you what your specific savings would be if you retrofitted with LED lights, and the tool takes into account those very things like the savings on the maintenance, the energy cost, and whatnot. And I think if you go to the solid state lighting page of the Department of Energy, it will direct you to those tools. You just put in what kind of lights you have, and it takes into account the cost necessary to do the retrofit and gives you your payback period.
Okay, excellent. So we have another downstream question. Are LED lights a significant factor in the heating loads of buildings, as the old incandescents do put out quite a bit of heat as opposed to power? So can you talk a little bit about how that might have an effect on the heating of buildings, if you have some thoughts on that, in addition to the electric efficiency?
So I've never, it does not mean it doesn't exist, but I've never looked at a study that discussed how that the LED lights, so LED lights are basically going to have no heating effect, positive or negative. Like clearly in Colorado in January, the old incandescents generating a little heat just helps offset some of your load, where now the LED lights have none. I am sure there is something out there that has looked at what that overall effect is. I mean, really, the amount of heat not generated is essentially the efficiency gains that you got, but I don't know how that affects your overall building load.
Okay, sounds like a great opportunity for a future study. And in the last couple minutes, there was a question about the supply chain and the risk. It seems very concentrated, both from the raw material stage as well as key parts of the manufacturing in the early part of the supply chain. So how is there a risk there, and how challenging would be if a country wanted to ramp up production of other parts of the supply chain? How challenging would that be for a country to do that?
So if let's say a country wanted to be fully vertically integrated and control all aspects, it would be very challenging, because again, all those rare earth materials that are necessary for the phosphors to down select the right color of light are all being processed in China. And so, and in fact, the rare earth materials that are listed are needed are actually not actually that rare, but the processing capabilities are, and it is all in China. And this can actually be very detrimental overall. For instance, in I believe it was 2012, China put export restrictions on phosphors, which then sent the LED market at the time tumbling because the countries making the packages therefore couldn't get the necessary raw materials. There are ongoing efforts to figure out how to manufacture an LED package without phosphors. You can do it by using multiple LEDs of different wavelengths and like combining their colors. So that kind of helps you overcome that one. It is very difficult to ramp wafer and LED die manufacturing, as these are essentially the same types of equipment that you need for making like any other semiconductors. So these are really expensive manufacturing wise. So there is somewhat of a hurdle there to ramp. And so you're looking at probably at least a couple year lead time if you're wanting to do a significant vertical ramp of that. Once you get to packages and luminaires, the equipment necessary is not that challenging to acquire. I mean, most of the luminaire is just a steel press, and so there wouldn't really be any problem.
All right, great. Thank you very much, Samantha. And we are ready to go to our next and final presentation. Last but not least, of course, we're going to talk about the energy, food, water nexus and some of the integrated energy research that we're doing to address agriculture and water challenges. And that will be presented by Jordan Macknick and James McCall. So Jordan, I believe we're turning it over to you.
Great, thanks, Jill. And I really wish we could all be there in person, but I'm glad this worked out for us to do this virtually. And so we look forward to telling you just a little bit about the work that we're doing, and then talking and fielding any questions you might have. Obviously, the ties between the energy sector and the water sector and the agricultural sector are vast, and we're not going to be covering all of that work and all those connections. But we're just going to give you a little bit of a snippet of some ongoing work that we're doing that I think highlights some of the great stuff that we're doing through JISEA and through NREL. So I'll start out, and I guess I'll start out first talking about some of the work we're doing that connects energy and agriculture, and then I'll be passing it over to James McCall to talk more about our work on energy and water systems. So on the energy and agricultural side of things, one of the things that we're seeing are some growing conflicts between energy development and land use. And one of this is due to the fact that solar has been booming. We need a lot, we'll need a lot of solar to be developed beyond rooftops on land. And this can take up substantial quantities of land that will see impacts and land development going across the country. This has been compounded by the fact that farm profitability has recently been declining, and we've seen a lot of solar developers working with to put farm projects on agricultural lands, which has led to some pushback and some concerns that we're going to be losing some of our prime agricultural lands to solar development. So one of the areas that we've been exploring is a unique and innovative solution to this, which is called agrivoltaics. So that's combining agriculture with PV to get agrivoltaics. And I think it's a great way to think about it is that we're harvesting the sun twice. We're not only producing energy, but we're using that sunlight that's either passing through the panels or reflecting off it or getting around it to provide some other benefit towards agriculture. And another motivation is some people might see utility scale solar projects that look like this and think that used to be prime agricultural land. We're looking at transforming those sorts of images to images that really highlight the benefits that we can bring to agricultural lands, whether it's through improving soil or improving yields in nearby lands, or actually through growing crops themselves. Our long-term vision is really that all utility scale solar projects could incorporate some element, whether it's pollinator habitat, wildlife, agricultural operations, or grazing operations, in a way that actually serves to benefit local economies and local agriculture rather than the opposite. To do that, we have a project that's funded by the Department of Energy that involves a lot of industry partnerships called the Inspire Project, where we are looking at these exact things. We're looking at how do we reduce the impacts of solar development from the get-go? How do we incorporate pollinator and native vegetation on sites? And then how do we integrate these with, these solar projects with ongoing agricultural operations? Here's a bit of an overview of the Inspire project. Some of the work we're doing is focused on looking at the economic viability of combining solar and agriculture. We're looking to see how these co-location configurations could actually increase yields in arid environments. We're looking at how these configurations can provide energy, water, and food security in remote off-grid areas. And then we're also looking at the broader ecosystem, ecological soil, and other pollinator habitats from these systems. We have about 25 sites that we're doing field tests on, located across the country. Here's a little bit of a snapshot of some of them. Each of these sites is focused on a different element, whether it's growing native vegetation, whether it's growing crops in between rows or crops underneath panels, or evaluating soil characteristics or redistributing water. We're trying to really capture a wide range of different opportunities where unique configurations and unique operations can have this benefit of really supporting improvements in agriculture and improvements in the energy sector. So for each of these sites, we are bringing standard protocols that we've developed in order to make sure that what we're doing is not relevant only for the individual site, but it has broader implications, and some of these insights can be replicated and can be transferred across sites. So we've in some sites we're installing detailed instruments. We're doing insect studies, and then we have standard protocols for how we're measuring vegetation. Some of the fun examples and fun insights that we're seeing is, when we are growing crops underneath the solar panels, we can see some clear outcomes. And so here's an example from our work at the Massachusetts test facility at the UMass Amherst campus, and where one example, we're growing broccoli underneath the solar panels, and you can see in the right figure, depending on where we place that broccoli plant underneath the solar panels, we will get broccoli crowns, as big as your head or about as big as your fist. And so these sorts of insights are really interesting. I think one of the more prominent outcomes that we've seen is from our research site at the Biosphere 2 facility in Arizona. Here we are also growing agricultural crops underneath elevated panels, a wide variety of crops, and we recently published a paper highlighting some of the exciting things that we're seeing in this arid environment. And one of those is for food production. So we grew peppers and different types of peppers and tomatoes underneath the arrays. And you can see here, we're comparing growing these crops in the open air versus under the partial shade of the panels. And you can see we've got almost 3 times the yield for the chiltepin peppers, about the same yield for jalapeno peppers, and about double yield for tomatoes. Combine that with the fact that we are saving water by having these partial shade conditions, and so we're needing about half as much water for peppers and about 1/3 as much water for tomatoes. And so this is we're seeing both the food benefits, the water benefits, and of course we also are seeing energy benefits too, because these agricultural crops create cooler microclimates underneath the panels. And so what happens is that we actually see lower temperatures during the day and higher temperatures at night, but those lower temperatures during the day when the solar panels are operating means we're getting about 2% more energy output from these arrays because of that vegetation underneath the solar panel, as opposed to panels that would not have any vegetation underneath of them. We're also seeing a benefit in our carbon uptake from this site as well. So really the Arizona site highlights we can get food, energy, water, and carbon benefits from this unique configuration. We're not limited to only agricultural crops. We are also exploring opportunities for and benefits of having sheep graze as well as cattle grazing underneath some of these elevated panels and some of these co-located systems. And we're measuring soil carbon and some other factors to see how these types of operations can benefit the soil and soil conditions. We're also doing a wide variety of field studies and analytical studies focused on pollinator-friendly solar. So if you plant a solar array with pollinator-friendly solar, or lots of nice flowers, we can see how that impacts local insect populations as well as local agricultural yields for pollinator-dependent crops. And this is also something we're doing in conjunction with apiaries or beekeepers to see honey production opportunities that could also accompany these solar projects. We have been working on integrating solar with greenhouses to see how that could affect yields, and we've seen some promising results in terms of increased yields when we integrate solar with greenhouses. And it also has ties into floating solar, where you could see evaporation benefits from putting solar panels on agricultural reservoirs. Beyond the scientific outcomes and the economic outcomes that we've seen, I think a big benefit of what we've been doing has been, and one of the broader implications is that we've really been able to work with a wide variety of universities, state and local agencies, and companies to really make this an educational activity. And it's sort of by necessity, it's been an educational activity where we've had to talk about the possibilities for integrating some of these agricultural activities into solar development. This is really a bright, new, ripe field that hasn't been studied much, and so a lot of the work that we're doing is sort of first of its kind, and we're working with very forward-looking companies, and so they're able to implement some of these practices in their new projects because they're seeing some financial benefits towards these low-impact approaches. And then we've also been able to work with state agencies who are trying to address, the big boom in solar that they've been seeing. It's been happening faster than what they were anticipating. And so working with them on some appropriate ways to manage that development in order to lead to outcomes where we could potentially see benefits not only for the solar development in that state, but also for the agricultural activities in that state. So that's a brief overview of our agriculture and solar work through the INSPIRE project. I wanted to pass it over now to James McCall to give a brief overview of some of our work integrating energy and water sectors.
Thanks, Jordan. If you want to go to the next slide. This slide is presenting our webinar required Sankey diagram, but basically this is showing that kind of energy and water are interconnected, both from an upstream side, which is basically energy production requires water, both in thermoelectric cooling, hydropower, but also extraction, mining, fuel production, also emission controls. And then also, energy requires water, and then water requires energy, both for pumping, treatment, transportation, and also heating and use. Basically just showing that there is this interconnection, and that a reduction of energy use in water or water use in energy kind of has some dual benefits across the nexus. Next slide. We're also seeing that there is some vulnerabilities to conventional power plants, conventional thermal or hydropower plants, from not having enough water, or the water being too warm to actually fulfill the needs of the plant for cooling. And so we've seen basically this map is showing over the last 15 to 20 years, sometimes that a plant has either had to shut down or curtail their electricity due to a lack of water or water temperatures. And in a changing climate, we see that this has a potential to kind of increase the risk over time. Next slide. Also, that there is a primary energy embedded in the water infrastructure. So basically energy use for water in the residential, commercial, or industrial sectors is roughly 13% of the total energy use in the US. So it's a fairly significant piece, both for water heating and also treatments and other industrial uses. Next slide. So part of this, we wanted to use this time to kind of announce our next big kind of research project. It's a 5-year kind of energy water desalination hub from the Department of Energy's Advanced Manufacturing Office, looking to address the water security issues and economic competitiveness across the economic sectors in the United States. And if we can reduce both the costs and then the energy use in the water sector, then there'll basically be dual benefits across that. We're going to be focusing on some early stage R&D projects for water treatment technologies and also ways to treat non-traditional water sources to free up some water resources to be used in other uses, such as agricultural, municipal water reuse, and industrial water reuse. Right now, we have a fairly broad research team, but we are looking for other partners to be involved in the water technology roadmapping activities coming up this year. So if you have any interest in that, please reach out to Jordan Macknick at the email address right there. Next slide. So that was just kind of some background information, and then we wanted to go over some of our past research that is very specific to kind of JISEA, and it's mainly around kind of water use and also water treatment within the oil and gas sector. So we have some projects currently that are current and past projects that are looking at, so what are the kind of key principles for effective water management across the life cycle of unconventional or hydraulic fracturing oil and gas operations. And as we can see from the graph below, from an EPA study, is basically this across this spectrum of water use in the unconventional oil and gas sector, there is water kind of touches each of these different steps, from where do you source the water, how do you kind of manage your water and chemicals on site, how do you make sure that the water stays where you want it to stay, and then how do you actually deal with the water once it's been produced. And then we also have another area of research looking at the characterization of water intensity, basically how much water is used per well based on the location, geology, and water usage. And then a final area is looking at kind of almost a techno-economic cost modeling tool to see if you have a certain amount of water at a certain type and other kind of characteristics, how does that actually affect the cost of treating that water? So next slide. So this slide is basically trying to highlight the fact that across all these different areas of water handling or management on the well site, from water sourcing all the way through produced water management, basically decisions that are actually made upstream have a fairly large impact on the other downstream. So basically from the water sourcing perspective, which is everything in the blue right there on the top right, it's actually impacted by all of these different kind of highlighted areas, such as cost of trucking, cost of storage on site, what is your well density and layout, and then what is the cost of treatment and also reuse. And so basically showing that there is kind of this systemic approach is necessary to effectively characterize these costs and optimize how you actually use water. And there's inherent variability in water quality and quantity across these plays, as kind of shown in the bottom right. So this is just a snapshot in time of these different prominent hydraulic fracturing plays, and kind of showing how much water is actually used per well and where these different sources come from. And this is heavily dependent on the timing of the field. If you're earlier on in the site, there might not be as much water to actually reuse in hydraulic fracturing. And as that field ages, then you kind of reach this tipping point to where now you actually have too much produced water. Now you have to figure out what to do with it. So making sure that is kind of incorporated into your water planning up front is very important. Next slide. This is also kind of showing some just kind of our produced water management tool, basically showing that after the water is produced and the oil is separated from the water, then kind of what are you going to do with it? And it shows this kind of pathway of basically at the top is, can you actually treat it on site for either reuse or for some other use, such as industrial, or in certain areas, maybe not as much unconventional agricultural reuse or beneficial reuse. And it's basically showing kind of these like complex decisions, such as the produced water quality and quantity, what is your desired end use, what is the cost of water available, and then also kind of what are the disposal well distances and other restrictions. And a lot of this work is going to be incorporated into that National Alliance for Water Innovation Hub earlier. So this will kind of be incorporated and used as we kind of develop some more of these cost models. Next slide. And then kind of a final just highlight of some of our oil and gas water work within JISEA is NREL had participated as a steering committee member for the California Council of Science and Technology's SB 1281 review. So basically, SB 1281 established new water reporting requirements for California oil and gas operators. It was meant to be an independent review of the data collected value and the usability, but also while balancing the burden on operators. When we were talking to operators, there were some concerns that in particular at the beginning, that the amount of time and personnel efforts put into this was by far exceeding the value. And so this project basically tried to see kind of what is actually the actual value of the data set. And the point of this was basically to try to, in particular in California, was to try to limit the impact of water use in the oil and gas sector on a drought-stricken area. So it was also trying to kind of assess what is the reuse potential of some of these like water uses. There are certain operations within California that are currently utilizing very clean or relatively clean oil and gas produced water, and then blending it and treating it to the point where then they're applying it to agricultural crops, and the amount of testing. And so it's basically seeing, are there other water sources available for that, and how do you balance the cost plus also the societal impact on kind of using that water. So it's kind of what is that trade-off. And then finally, it's making sure that this data set actually does what the intent was, is to kind of how can we manage and identify the risks to human health and the environment posed by all of these different water uses. I would like to be able to share more with you about this study, but it's still under review. And so I would just say, look for that in the future. And yeah, and that's, I think, all that we had so far. So thank you. And are there any questions?
Thank you very much, Jordan and James. We do have a couple questions. The first one is regarding the agrivoltaics. Is this an international study, or how are you collaborating with others in Europe, such as Fraunhofer in Germany, who have also been working on agrivoltaics?
Yeah, that's a great question. The primary focus of the Inspire work and the location of our field sites are all in the United States, but we certainly recognize that there is a lot of great work that's going on, not only in Europe with the Fraunhofer, but also in Japan, and in China, and there's many other locations within Europe where this is happening as well. And so we do our best to engage with them as possible. There was in the first ever agrivoltaics conference has been scheduled this summer in France. I cannot say if that has been canceled already or if it will soon be canceled, but that was going to be a first opportunity to have the first international conference on this. But I think it's important to note that we are aware of what's going on internationally, but we haven't yet had an official collaboration or a collaborative project with them. It's just been more exchanging of information and engaging with the folks that are doing this across the world.
Okay, excellent. Yeah, it seems like there's lots to learn from each other on that. And this, I would say, is a related question. Could you spin off a new venture to implement this type of water and energy work around the country? So to like an NCAR or UCAR type of arrangement. And I would say this might be a question that's both related to the agrivoltaics as well as the industry produced water. So maybe you can answer it for both of those. So Jordan, maybe first on the agrivoltaics.
Sure. Yeah, I think there's no shortage of new ventures or new opportunities that could arise from agrivoltaics, and this is both, something that is relevant for that would be related to solar developers, as well as something relevant for water managers, as well as something relevant for agricultural entities. And I think a lot of the work that we've been doing and demonstrating certainly has the potential for making a very strong business case that this is a way in which you can, not only produce higher yields for some crops in some areas, but while using fewer resources as it relates to water, and also helping to improve the soil. And then you also have the opportunity for sort of marketing and having a value added marketing approach to say, these are tomatoes that are grown, by the sun, or solar powered honey. There's a lot of certain opportunities there. We haven't yet seen any companies beyond those that are developing the energy systems really make a strong effort to do this. I think that certainly is a possibility. And I also, the one area where we have seen many startups and many companies do this is with basically the solar powered honey activities. So we've seen a lot of beekeepers keep their hives near pollinator friendly solar arrays, and then they're able to sell their honey framed as it being solar powered. And so, but I think there's certainly more opportunities, and as this becomes bigger, and certain states such as Massachusetts that have explicitly encouraged these sort of co-location configurations combining solar and agriculture, I think we're likely to see many more new ventures and many more new opportunities for people to really capitalize upon the outcomes that we're seeing with our research.
Great. And James, any thoughts on new ventures for your part of the presentation?
Yeah, I think a lot of the themes that kind of Jordan just touched on are very similar. I know from the produced water kind of treatment and management side, there is no plethora or no shortage of kind of technology companies that are trying to kind of meet this market need. There's just various different things, and kind of a lot of companies are in this kind of pilot phase where they're trying to see kind of how can they incorporate this into their operations. But I think that there would be a lot of value in kind of taking a look at how do we make it so if this water is going to be used for other purposes, that both kind of consumers and regulators kind of are satisfied that this water is going to be usable for their application. And I think also oil and gas companies, what we've heard from them is they are approached by technology vendors, many times a week, and kind of making sure that there's this testing procedures in place to validate that this technology is going to do what the vendors say that it's going to do, would actually provide a value to them, and would also kind of reduce that burden of getting approval to incorporate that into their operation. So that would I think probably more on that side for the produced water.
Great, thank you very much. And I think we are at time, so thanks to James and Jordan, and thanks to all our speakers, and thanks to all of you attending. Just want to note that when you do leave the webinar, you will get a survey. I hope you fill it out and give us some feedback on how you like this type of meeting, if you like all these types of presentations together in one forum, or if you would prefer shorter sessions with more individual topics. We're looking for feedback on how to do these types of sessions going forward. And also, please feel free to visit our website, check out our new annual report, and lots of these reports are online or coming soon. And you can follow us on our social media to get that information. So thank you very much, and thanks for attending.